Okay, so today we will continue to look at the Vesper theory, but this time we will go and add a little bit more. And this is intermolecular forces. There are some intermolecular forces that affect all the molecules that you come across. Now, what are they? We're about to find out in this PowerPoint right here. This PowerPoint, not the other one, I like this one better, is geared towards you finding out what these forces are and how they apply. So let's go look at them. All right, so what is an intermolecular force? An intermolecular force is an attractive force between molecules. Not to be confused with intramolecular force, which is a force that holds the atoms together in a molecule, or to put it simply, the bonds that form between atoms that create molecules. If you compare the two, intermolecular forces are much weaker than intramolecular forces. For example, it takes 41 kilojoules to turn a mole of liquid water into a gas. But it takes, and that is the intermolecular forces, but it takes 930 kilojoules to break all the hydrogen-oxygen bonds in 1 mole of water. Those are the intramolecular forces. As you can see, this is a number that is more than 20 times it's, the other one. So that is a big difference. So this is a true statement right here. Intermolecular forces are much weaker than intramolecular forces. Now, how do we measure these? How do we know that these exist? Well, this is how. We have boiling points, we have melting points, we have heat of vaporization, heat of fusion, and heat of sublimation, among other things. And this is how we know the intermolecular forces are at play. Another thing is, you've ever looked at a protein and, this was an alpha helix configuration of a protein structure. The amino acids within this structure make it fold the way it does because of their properties. And those intermolecular forces are at play when that happens. So basically, the specificity of enzymes is given to them by the intermolecular forces contained in their amino acid chain, which folds them a certain way. Another thing that you can think of is the crystal structures in a cave. Those are beautiful. Well, this is what gives them their structure, is their intermolecular forces. Snowflakes, the shape of snowflakes also. And you also have all these other properties, surface tension, density, all of that also are part of this intermolecular force network. Now, DNA, you know how there's an alpha helix? Well, the reason it coils like an alpha helix is because of the intermolecular forces that are between the two nitrogenous bases. Remember, A goes with T and C goes with G kind of thing? Okay, so those intermolecular forces join those two molecules together, but not as a bond, is a hydrogen bond. And we'll look at more about that in a minute. Okay, so these are the 4 forces that we're going to cover today. London forces, to begin with, are forces which are present only because basically there is an electron cloud present, and there is an electron cloud present in every atom, and atoms form molecules. Therefore, there is an electron cloud in every molecule. So it doesn't matter if you're polar or nonpolar. All of these are going to be dependent on several things. So the intermolecular forces known as London dispersion forces happens due to the electron cloud. So whether you're polar or nonpolar, doesn't matter. What matters is how easily that electron cloud is distorted. And you notice it says the larger the molecule, the greater the dispersion forces are. And what did this dispersion forces do to a molecule? Well, they do the boiling point. Right here, I'm sorry, I forgot to point this out. This right here is something that we've already learned. Do you remember atomic size? Well, it increases to the left and down in the periodic table. So that means that fluorine, which is higher, is less polarizable or less distortionable than iodine, which has a much larger electron cloud. Fluorine is at, well, actually it's over here at the top over here. Then you have chlorine, right? And then you have iodine, or maybe there's another one, bromine. Yeah, bromine, I think it's next, and then iodine. So as you can see, iodine would be much larger than fluorine. Therefore, it is easier to disturb its electron cloud. Hence, you have higher London dispersion forces. So that's how you know. There's other things that you need to know about these, how to measure them. Okay, another thing is the boiling point of alkanes, and this is a type of organic molecule, alkanes. Basically, they're just carbon and hydrogen, and the carbon chains, in other words, how many carbons are in it, is what gives these molecules their boiling point. The larger the molecule, or as in the more carbons it has, the higher the boiling point. As you can see, decane, which has 10 carbons, is 174 Celsius, whereas pentane is only 36. Pentane with 5, I mean, is only 36. So it does increase dramatically. All right, another thing to look at, and we've already looked at with these, greater number of electrons, we saw that one. Number 2, more diffuse electron cloud, that means larger size. Another thing, molar mass. Molar mass, we haven't yet found out what that is, but it's basically just adding what's there. So if you were to do the molar mass of carbon and 4 hydrogens, which is known as methane, the molar mass of methane is the mass in the periodic table, which is 12.01 of carbon plus 4 hydrogens, so 4 times 1.01. That gives us 4.04 plus 12.01 gives us 16.05. So that's a very low mass, molar mass. Whereas over here with iodine, you know iodine is a huge molecule, I mean a huge atom, therefore it weighs a lot more, and because it has more protons, neutrons, remember all of that. Okay, so then this molar mass would be much greater. So look at the difference in boiling points and melting points. I mean, 125 negative 85, sorry, I don't know, 82.5 and 171. That's a big difference. It's more than double if you're looking at just the numbers. All right, so the next thing that you need to look at is the other force that's coming up, and that is, remember we looked at how to tell if something is polar by doing the Lewis structures? Well, this is why. You need to know if the molecule is polar to know if it has a dipole. Polar molecules all have dipoles. What is a dipole? Basically, an imbalance of charges caused by a more electronegative atom being present in the molecule, pulling their electrons closer towards itself. If you look at your periodic table and you recall how this increases actually this way, which is left to right and up the periodic table, finding fluorine at the very top. So fluorine is the most electronegative molecule. Then you have oxygen. Then you have, what is here? Oh Lord, I'm trying to think. Nitrogen, sorry. And then carbon right here, okay? So you can see the next closest electronegative would be oxygen. And then sulfur is down here. And then chlorine's right here. So chlorine and oxygen are very electronegative. The most, of course, is fluorine. And this is what the direction of the dipole is based on this chart. That's why it's important to know this. Remember, I told you this was all going to be applied at some point, and here it is. All right, so in this case, hydrogen is much over to the left, right? So it's lower in electronegativity. So the oxygen, which is more electronegative, pulls those electrons closer to itself. And if you know anything about physics and remember how to do vectors, which is what these are, vectors are quantities that have both magnitude and direction. So if the direction is equal and opposite, they are going to cancel. But these two are not. These actually are going towards the same place, therefore, and they're going up. So their dipole moment is going to be measured by that, the addition of both of those. And that is going to be a direction of going towards the oxygen. So that is a dipole moment. This one right here, if you look at the dipoles, which carbon is less electronegative than oxygen, as we saw in that diagram that I made real quick, you can see that the imbalance is going to go towards oxygen. So oxygen is going to be our negative. Oh, I forgot to write that down on here. Our oxygen is our negative here, right? And our hydrogens are our positives because the electron cloud, and I mean, I'm not saying they're positive, like they have a positive charge. They have what is known as a partial positive charge, which means there's an imbalance. In this case, here, carbon is going to be your positive and the oxygens are going to be the negatives because that's how it works. But they are pulling at the same place. You see that? The same magnitude and direction. Therefore, they add up to 0. And that's why vectors need both magnitude and direction. All right. And so that makes it a nonpolar molecule. The next one that we have is SO2. And remember, sulfur is more to the left of oxygen. Therefore, it is less electronegative. Again, that would be your positive sulfur, and oxygens would be your negatives. And in this case, the imbalance is not superimposable, as in they don't have the same magnitude and direction, an opposite direction. In this case, yes, they do have the same direction and the same magnitude. So they add up to a larger vector going down. And the last one that we have is, this is methane, and carbon is more electronegative than hydrogen. Therefore, carbon gets the negative and hydrogens get the positive, but the hydrogen movement is all opposite and they will cancel. If you notice, the upper and lower are going in the same magnitude but opposite direction, so they will cancel out. It's like saying 2 plus -2 equals 0. And so are the ones that are in the horizontal plane. So that gives you a nonpolar molecule, no dipole. Okay, so that's how we know. When they're nonpolar, they have no dipole. When they're polar, they do. Attractive forces between polar molecules. Okay, so this is important too, because this is how crystal structures are formed. The orientation in the polar molecules form these lattices or these structures, let's put it that way, cubes or whatever, that are going to make a connection between positive and negative of the same molecule. Right here, this guy right here, all four of the carbon groups, the carbon is bonded to all 4 methyl groups. They're all methyls. So basically, they are going to be pretty much a how would I say, less polar, as in non-polar. Whereas these other ones, which have one that is different from the others, right, is going to be polar. And that's how we know, because they're not symmetrical. All right, ion dipole. Okay, so these happen only because you as an ion, right, or it as an ion has a charge, and the charge is attracted to the dipole. So these are attractive forces that happen between polar molecules and ionic compounds. And ionic compounds are made of ions. Therefore, if you have a charge, you are going to be able to do an ion dipole when there is a polar substance present, like water. Okay, which brings us to our next slide, where you can see the dissolution of sodium and chlorine in water. So sodium chloride, right? That is your ionic compound dissolving in water. Water is attracting the chlorine, which is negative, to its positive area, which is the hydrogen in white, and sodium is being attracted, sodium ion is being attracted to the negative area, which is the red, or the oxygen. Now, that brings us to the last of our intermolecular forces, and it is the strongest. It is known as hydrogen bonding. It isn't actually a dipole moment, but it's a special type. It only happens if you have a hydrogen bonded to nitrogen, oxygen, or fluorine. It doesn't happen with carbon. It doesn't happen with any other, even though you have, and it has to be polar. That's the other thing. You've got to have a polar molecule, and it has to have a hydrogen to nitrogen, oxygen, or fluorine bond, like you can see down here. Okay. And they're usually represented by those dots. Those dots aren't real bonds, but they're very strongly attracted. DNA is hydrogen bonded to it in the middle area. The two nitrogenous bases, A and T, so they are going to bond to each other by hydrogen bonding. They don't really bond, but they do attract each other. And that's why we have the rungs in the ladder. All right here, this is benzoic acid, which is very polar. Look at the crystals. Let me point out one little crystal. See how long they are? The reason they do that is, you notice it says they have hydrogen bonding, and they stack in planes which are held together by dispersion forces. So they don't look like any other structure that you've seen, like sodium chloride, for example, which makes little cubes. These are long, and they look like planes, like lines. Yeah, and that's because they're stacking on each other. All right, next. Let's go to the next one. All right, so this is the final slide, and this is where I summarize what all of this means. Okay, so London dispersion are going to be present in both non-polar and polar molecules. You notice that in this case, so far, these are the only forces that are present in the non-polars, except for ion dipole, which you don't have to be a polar molecule to be an ion. You just have to have a charge. Dipole is got to be polar only. Okay. Ion dipole, it is an ion, so it's a charged, right? Charged atom and a polar molecule. So if you're, molecule. So if you're an ion, you are going to create an ion dipole, okay? So that's why we are going to say it's okay. Doesn't necessarily have to have polar, but it has to be charged. Hydrogen bonding, again, it has to be only polar, and only if the hydrogen is bonded to either oxygen, fluorine, or nitrogen. Okay? I should put a word there. Okay. All right. So that's the summary of all of these. These are how polar molecules work and nonpolar molecules work. So let's go back to our lab that we said we were going to complete. So let me go there. Escape this. Okay, so do you remember we had this up here? We were doing this one right here. Hold on, where are you? This right here, the Vesper lab. So I have answers to that one, so I'm going to go get those. I thought I had them open, but I don't see them. So maybe I can find them really quick under documents. So it's Vesper lab, and it'll say ANS. Enter. Okay, come on, let's find you. Okay, there we go. That's the one I want with answers. It doesn't matter. I just got them all. All right, so we have that one. I think that's the best one. And we are going to, well, if I leave that up there, it's going to be messy. So I'm going to go ahead and get rid of those. So that way you are able to see what I'm doing. So I hope you took notes because this is where it's coming. All right, so let's go look at our analysis. We did all of this already. All right, so we analyzed these 5 compounds. The only thing we didn't say was what? Forces. Okay, so look. If you're looking at this and you remember what we just wrote, nonpolar only have London dispersion. Okay, so we're going to call it LDF on that one. Again, nonpolar, nonpolar. So just copy that and paste it all the way through because all of them are going to have LDF. Every one of these. Every single one. Why? Because they're molecules. And like I said, polar or nonpolar, they all have them. How much? That depends on all those characteristics we looked at. But they're all going to have them, polar or nonpolar, like I said. I want to stress that out because it's very important. All right. Now, you notice over here, the only polar one is this one. So it's going to also have dipole, and I'm just putting the initials because it's a lot to write. And it is also charged. So it's going to have an ion dipole. See? There are no hydrogens, therefore there cannot be hydrogen bonding. So that's all we have on that one. Let's see if we match based on our analysis. Okay, so let's see our answers. Oops, sorry. Answers right here on the bottom. Look at that. They match. You see that? They match perfectly because we did the analysis correctly. Now, if your analysis is wrong, if your Lewis structure is wrong, all of this is going to be wrong. And so that's why I stress to know how to do Lewis structures. And I'm going to show you another little thing where you've got a little bit of a more of a tutorial on this. And I think you'll like that one too, but I'm going to show it to you at the end of class. Okay, so the next one that we have are these. Now look at these. Again, we have polar, nonpolar, nonpolar, nonpolar. But now we're a little bit more into what we can be. Okay, so this one is going to definitely have London. It's going to have dipole, dipole, right? Because it does have a polarity, but it's also a hydrogen bonding to an oxygen. So all these 3 forces are going to be attributed to this one molecule. What about the next one? Okay, so the next one is just going to have, okay, that's that one. This next one is going to have London dispersion forces and ion dipole because it is charged. Next one too, right? It doesn't matter if it is or not charged. Charged, polar. It is still going to have ion dipole possibilities because it is going to induce one if there is a polar molecule running around somewhere. Okay, so PO4 also not polar, so London dispersion is the only one, and also ion dipole. All right, now let's look at the last one. It says it is also nonpolar. So we're just pretty much writing the same thing in all three, right? London dispersion, forces, and ion dipole. And that's it. See, the analysis, the analysis gives us all of those answers. So you've got to know how to do the polar, nonpolar, polar, nonpolar, and then also look at the charges up here and what they're made of. So by knowing that this has a hydrogen-oxygen bond, we know that it has hydrogen bonding. All the other ones have charges, therefore they also have ion dipole. That's as easy as that. It is not a complicated thing to do. Let's clear these because, you know, the next ones are not going to be the same, and keep going to the next set. All right. And notice I'm not showing you until the end what the answers are because I want you guys to start thinking about it. Okay, oops, that one I accidentally showed you. Sorry, oh man. There we go. I don't want you. There we go. Now you can't see it. All right, so CO3 to negative. I'm just going to speak it this time. All right, so look at it. No hydrogen bonding. Not polar, can't be hydrogen bonding either. It cannot have dipole-dipole. See, we're eliminating. What can it have? Well, London, of course. Everybody has London. And what else? We have a charge. Charge, even though it's nonpolar, indicates we could have an ion dipole. See? All right, next one. Polar. Ooh, okay, but it's not charged. So it's not an ion dipole. However, it's polar. So we have London and we have dipole-dipole. No hydrogen bonding. Next one, it says it's polar and it's also charged. So you can induce an ion dipole and a dipole-dipole, and of course, London dispersion. The next one, polar again, not a charged one. So it's just London and dipole-dipole because there is no hydrogen bonding. The last one, nonpolar, the only thing it can do, and it's not charged or anything, so no hydrogen bond either. Well, they couldn't have hydrogen bond if it's nonpolar. So all of those are eliminated. The only thing it can be is London. You see that? And look, there they are. All right, and the last set, well, no, there's two more sets. No, this is the last set. The last set's the one that's the juiciest, because it's got all the stuff. All right, so let's look at them. Okay, so we have polar, polar, nonpolar, polar, polar. Man, there are all these polar ones. Okay, so what do we see on the first one? Okay, we say it's polar. So I mean, you know there's London, right? So London dispersion is there. Polarity means we have dipole-dipole, and we have a nitrogen to hydrogen bond. Therefore, we also have hydrogen bonding. Let's check the next one. The next one is also polar. So London dispersion, dipole-dipole, hydrogen bonding because we have hydrogen to oxygen bond, and we have a charge. So this guy has all three. This is the hydronium ion. All right, and it is very polar, and it has all of those properties. Now you're looking at NH4 and you're thinking, oh, there's hydrogen and nitrogen, and there's a charge. So this one's just like the other one, but no, because this one's nonpolar. Since it is nonpolar, it cannot have hydrogen bonding. It cannot have ion dipole. I mean, it can have ion dipole, but it cannot have dipole-dipole. So the only thing are London and ion dipole. The next one is polar. So it has ion dipole because it's charged, London dispersion because it's a molecule, and also dipole-dipole because it is polar. The last one, looking at it, you're looking at it and you're going, okay, so that one says polar, even though it doesn't have anything else, but you know that there's two ways of knowing how to do polar. In this one, The reason it's polar is because one of those atoms that is bonded to the carbon is not a chlorine. Therefore, it imbalances the charges. So it kind of would look something like this if we do a quick Lewis structure just to, oops, I don't like it when it does that. All right, so let's do it quick. Okay, so chlorine, and I'm not putting the dots right now because I just want you to see. Okay, so hydrogen and carbon, the dipole is going to move this way. The chlorine is more electronegative than carbon, so all these dipoles are going that way. So you see, none of these are going to cancel, right? Because there's nothing to cancel them with. You have a hydrogen to chlorine bond that is not going to cancel because these are more of a three-dimensional structure. So they pretty much have to be, you know, an opposite, exact opposite, and they're not. So all of these are not going to cancel. Therefore, we're going to have polarity. All right. So that's one of the things we know. All right. So we have polarity, which we already had determined, but I wanted to show you why we have polarity, even though we don't have a lone pair in the middle, and the 4 and 4 are the same. And the tetrahedral. So everything here points to the fact that it is not, but because it doesn't have an E, so it doesn't have an electron lone pair in the middle of, to the central atom. None of that. But one of them is different, so that's the reason. So the polarity in this one is going to induce dipole-dipole, as you saw, and is going to do London dispersion. There is a hydrogen, yes, but the hydrogen is bonded to carbon, so therefore no hydrogen bonding in this case. And it doesn't have a charge, therefore no ion dipole. And that concludes pretty much this particular one, right? And we are going to just check these answers right now and see how we did. See, there they are. And this is just showing you what this lecture is going to cover. So the last thing we're going to look at is the properties of water after we do this, because now we understand more about water, because we know water is polar and it has hydrogen bonding. So we are going to go back and look at this PowerPoint called, oops, sorry, that is a mess, called Properties of Water. And it is important to know the properties of water because this planet and us as in people and things are, things that are alive, I mean, are mainly water. And look at this. So we have all of these questions. I mean, you can read this. I'm not going to read it to you, but look at it. It says, should we control a chemical that does all these bad things? Okay. And it says, accidental inhalation can kill you, contributes to erosion. All of this stuff sounds bad. But the chemical is actually plain old water. Yeah. And if you think about it, accidental inhalation of water is known as drowning. So yes, it will kill you. And the effectiveness of car brakes, well, why does that? Because when it rains, your brakes don't work as well. The street's wet. All right. So this is why. And why are all these things possible? Well, let's see. Okay, the most common molecule in living cells is water. Most cells, depending on the type, are anywhere between 70 to 95% water. So basically, you and I are mainly water. And among that water, we're mainly empty space, but that's another discussion for another day. But anyway, the planet, if you look at the picture, all of this blue stuff is water, mainly water. And there are properties that actually keep us alive. And these are the ones we're going to look at. Cohesion. Cohesion, water sticks to water. That means that water attracts water. And that's because it's polar. And also hydrogen bonding. So mainly every answer that we're going to have is going to be hydrogen bonding. Water sticks to other molecules. That means that if something is polar, water is going to stick to it. Why? Because of hydrogen bonding again. If you've ever looked at a tree and wondered, how does the water get all the way down there from the roots? Because that's what absorbs water, right? The leaves don't. They actually expel water. So if you look at it, you're going, how does that water get all the way up there? Well, they don't have a straw. So, well, you kind of do, actually. That is what this is. This set of vessels, capillary, well, sort of capillary. It's a little conduction system that the plants have for water is charged. So the walls of it are charged. So the water gets attracted to it through adhesion, and the water attracts other water. So through capillary action, right, from the adhesion and the cohesion, both water sticking to water, they go as one goes up, each molecule of water goes up, makes it higher and higher and higher and higher and higher and higher until it gets to the leaves. And water is replaced as transpiration occurs. As you know, when plants exhale their carbon dioxide and water, right, they lose some of that water, and more is absorbed through adhesion cohesion again. So that works. So it is important to know. Also, water has a very high surface tension. Surface tension means that the surface of the water is hard to break. If you've ever belly flopped on a pool, you know this, because it feels like it's solid, but it's liquid. So it is very hard. And that's why this little bug is standing on that water. It also has a high specific heat. And this is the definition of specific heat. And the reason it's this, normally something that has a high specific heat is because they're large. And this is not a large molecule, it's a tiny, tiny molecule. But it acts as a large molecule due to that hydrogen bonding. So it looks, it acts, like I said, as a high. So it is high specific heat. So it takes a lot of heat to increase its temperature. And that's a good thing. Let's skip that. Okay, so that means that water stabilizes our temperature. And that is why we always look for water to see signs of life in other planets. Have you noticed that? Yep. That's one of the main things that they say, oh, they had water, so they must have had life or whatever, So far, there hasn't been, except I think Mars had a little bit of frozen water, and that's one of the things that people think maybe something happened to it and there was life somewhere. But anyway, it doesn't matter. The point being that we have climate moderation, which means that we don't get too hot or too cold, and we're able to survive those changes. Another thing, it is high heat of vaporization. That means the water absorbs a lot of heat in it to change into a gas. That is why evaporative cooling exists. And we're not the only ones that do this. A lot of animals are sweating and they sweat because it cools us down. And how does it cool us down? Well, water exchanges the heat from our bodies onto itself, right? It pulls it out and it evaporates. And as it does that, it's absorbing our heat. Therefore, it's taking our temperature down. The result, again, this is why most of us don't get heat stroke easily. Now, we do have to keep hydrated. There's the word, hydrated. Water, water, water. See, there it goes. all the time. They always tell you, if you're out in the heat, if you're going to be out in the heat, keep hydrated. All right. And that's why. Another thing is it has a very weird property. If you freeze water, instead of decreasing the distance, it increases between molecules. And that is because of the hydrogen bonding. There's a picture of kind of like a representation of that hydrogen bonding happening in a frozen state. You notice how it's larger than the one in the liquid? And that is why ice floats in water. And no other molecule that I know has that property where its liquid is less dense. I mean, more dense, sorry, than its solid. Look at benzene over here. See how that's the norm right there. If it's a solid, it's going to sink in its liquid. But ice does not. And that is the reason why these little guys stay alive. Because if you think about it, if ice started from the bottom up, it would freeze 100% at lakes, oceans, maybe not so much oceans because they do have salt, but lakes, rivers, oceans, all of them would freeze completely. And that would mean the death of all aquatic life. And there is not a death, not even in the up there, way up in the North Pole. We still have, and the South Pole, we still have critters in the water. And this is why. And it actually helps it because it insulates them. So another property is water is very good as a solvent because it will form a solution with almost anything. But there is a key to this. When you have water, which is polar, you have to remember that like dissolves like. What does that mean? That means that polar dissolves polar and nonpolar dissolves nonpolar. Water and oil don't mix. We know that water is polar, therefore oil must be nonpolar. That's right. So you have to remember this little tidbit here. So an ionic compound is charged, therefore an ionic compound will dissolve in a polar substance very easily, but it will not in a nonpolar. You see? So that works. It works beautifully. All right, and that is basically all of the properties that I can think of water that you need to know. Yep. Yeah, all of this we already looked at. And you know hydrophilic and hydrophobic, that just means, all right, so the last thing that I was going to point out is there is a thing called the cell membrane, and you know this one. And you know that our cell membrane basically, okay, I'm going to make a shape, but it's just, okay, there we go. It's mainly, I'm just doing this, but you have phospholipids, and the phospholipids have tails, right? And those tails, we know, are hydrophobic or hydrophilic, either one. Okay, well, oh, nope, I don't want another one. Undo. Nope, I meant, I clicked on this line and it didn't take it. Okay, pin. There we go. All right, so you have these tails, right? They have kinks in them. And I make them a little too long, but that's all right. And they're to the inside because this is the hydrophilic area of the phospholipids in the membrane. And this right here, which are the tails, notice that it's facing, if this is the cell membrane, right here, right? This is the outside of the cell, and this is the inside of the cell. But they both face to the outer, right? So that's these are the hydrophilic. The tails are facing away from the water, therefore they're the hydrophobic part. So remember that. This is a very important thing. So the hydrophobic tail, this one is called a phospholipid because this is the phosphorus. Remember, phosphorus is charged, right? And the lipid, look what it says. Lipids are nonpolar. Therefore, they're going to be hydrophobic. And they're the lipid tails. Therefore, they're hydrophobic. All right. So that concludes pretty much this lecture for today. You guys have a wonderful Thanksgiving, and I will talk to you next time, which will be Monday. Yes, I know it was a very short-lived break, but it's okay. All right. Take care. Bye-bye.